So let's take a look at one more example. Here we're going to actually have 3 different states, and this is for a herd of American buffalo, or bison, which can be modeled by a stage matrix similar to that for spotted owls. This was a different example from somewhere else, so don't worry about the spotted owls. The females can be divided into calves up to 1-year-old, yearlings 1 to 2 years, and adults. So basically every year calves are going to become yearlings. They can't stay calves because that's up to 1-year-old. And then every year yearlings, the ones that survive, well, that's just from time 1 to 2. So at time 2 they become adults. Suppose an average of 42 female calves are born each year per 100 adult females. Only adults produce offspring. Each year, about 60% of the calves survive, 75% of the yearlings survive, and 95% of the adults survive. For k greater than or equal to 0, let x sub k be the state vector that contains the calves, yearlings, and adults in that order, where the entries in xk are the number of females in each life stage at year k. So we're not modeling adults, we're just modeling female bison. And so let's start off by building a state transition diagram for this. As usual, we're going to set up our states, which in this case we have 3 of them. So we'll have the calves at time k plus 1, the yearlings at time k plus 1, and the adults at time k plus 1. And so we know that each year about 60% of calves survived and they become yearlings. 75% of the yearlings survive, so they're going to become adults. Oh, and 60% of the calves at time k will become yearlings at time k plus 1. 75% of the yearlings at time k will become adults at time k plus 1. 95% of the adults survive, so that tells us that 95% of the adults at time k remain adults at time k plus 1. And if we really wanted to, we don't have to do this here, but if 60% of the calves survive, that means 40% of them do not, and 75% of the yearlings survive, so 25% do not. And same thing here, but this is going to be 5% of the adults at time k do not survive. So we don't really need these pinkish vectors at all. Those are just telling us that some of these animals bison are leaving the 3 states. So if we wanted to start a 4th bucket, we could say deceased, but that's not necessary. We don't want to keep track of those. We want to keep track of the living population. And also, we're told that 42 female calves are born each year per 100 adult females. So like our last problem, that means only the adults are going to contribute back to the calves. Now you can imagine that if we didn't have this arrow and there were no bison being born, eventually all the calves would become yearlings, which would all become adults, and then progressively those adults would die off at 5% a year. But we are getting 42, this is 42 per 100, so that means 42 calves per 100 adults. And we need to multiply that by how many adults we have at time k. So if we had 100 adults, that means we would get 42 new calves. And so we can just write this as, and remember this is in, the units of this are adults, so the adults would cancel out, and that tells us the number of new calves. And 42 divided by 100 is 0.42, so we can just say 0.42 a sub k. So now we're ready to build this model out, the recursive system of equations. And so we said that the number of calves at time k plus 1, well, none of the 0% of the calves at time k remain calves. 0% of the yearlings at time k become calves. But then we know that every adult will give birth to 0.42 offspring times the number of adults there are. We don't need to worry about this being fractional at this point. We're really just interested in investigating long-run behavior anyway. The number of yearlings at time k plus 1 will be the calves that survive, and so that number up here came out to be 60%. So the only way for new yearlings to become is for calves to survive, and that's going to be 60% of the calves at time k become yearlings at time k plus 1. None of the yearlings stay yearlings, they transition to adults, and none of the adults at time k become yearlings. The number of adults at time k plus 1, well, that's none of the calves can go straight to adults. They have to become yearlings first. We know that 75% of the yearlings at time k survive to become adults, and we also know that 95% of the adults at time k remain adults at time k. Now you can hopefully see what our coefficient matrix is going to be here. Short of writing it out, we're going to be able to see that the A matrix, in this case, the transition matrix, will be 0, 0, 0.42, 0.6, 0, 0, and 0.75, 0.95. So as you guessed it, we're going to now we're going to look at the eigenvalues and eigenvectors. I think we're going to skip over this question here. Find the eigenvalues and eigenvectors by using appropriate technology. Use the diagonalization vector decomposition theorem to provide equations for each of the three groups, calves, yearlings, and adults as a function of t. So no initial condition is given. And we note from the previous problem, our little observation, that really all we needed to look at was just the eigenvalue and eigenvector corresponding to the dominant one to determine what happens in the long run. So let's go ahead and write out x sub t. So for k1, k2, and k3 in this case, because we have 3 eigenvectors and 3 eigenvalues, we're just going to write out x sub t is going to equal k1 times lambda 1, which is 1.10 to the t power, times v1, which is 0.38, 0.21, and 1. Okay, now look at lambda 2 and lambda 3. We have an imaginary number in there, and I, if you recall, is equal to the square root of -1. If you remember when we found eigenvalues and eigenvectors, we had to solve a polynomial, and we solved quadratics. This is pertaining to a cubic, but it's possible to have non-real roots. So this is exactly what happened here, and so we might panic and say, well, how do we write that? You know, we could start to write plus k2 times the eigenvalue, which is -0.08 plus 0.41i times v2, right? And it's going to have its 3 components, and then do plus k3 times the third eigenvalue, which is -0.08 minus 0.41i times the eigenvector 1, 2, 3. But we're going to make the argument here that lambda 1 is dominant. But how do you do that? How do you determine that this is dominant when these guys contain imaginary components in them? So I'm going to state this without giving it much proof, because we would have to do some complex analysis here dealing with complex numbers. And you can see that even the 2 eigenvectors corresponding to the 2 non-real eigenvalues have i's in them as well. So we don't even want to write those down. It's going to get too messy. But here's the thing. You can say that a real eigenvalue is dominant to 2 complex eigenvalues as long as the magnitude of a complex number, where the way you find this, again, this is a result from complex analysis, so you don't need to worry about why this is right now, but the magnitude is just the square root of the component squared. So if that number is smaller than the largest real eigenvalue, then the real eigenvalue is dominant. And so you can see that A and B, when they get squared, they'll both be positive. So let's just verify this. So the magnitude of lambda 2 is going to be the square root of -0.08 quantity squared plus 0.41 squared. And if we do that in our calculator real quick, I didn't have this computed, let me compute it real quick here. But you can tell that that number is going to be much smaller than 1 because we're taking the square root of decimals squared. And that comes out to about 0.42. And you can see that that is less than 1.10, which is what lambda 1 is. Lambda 3, its size, is going to be basically the same thing, negative 0.08 squared, plus negative 0.41 squared, which comes out to the same thing, which is still about 0.42, and that's also less than our dominant eigenvalue. Therefore, we can say that as t approaches infinity, so I'll write that down here, as t approaches infinity, this term here will become negligible, as will this K3 term here, that will also become negligible. And so we can say that x of t becomes approximately so as t approaches infinity, x of t is approximated by, I'll just say approximately equal to k1 times 1.10 to the t times the vector 0.38, 0.21, and 1. And so what that means is that first of all, this is telling us that this vector will ultimately point in the direction of v1, and every additional time unit, the components will grow by 10%. So this means that if this is the number of calves at time t, or I shouldn't say calves at time t, but the ratio of calves to yearlings to adults, I could say that for every 100 adults, I'll have 38 calves and 21 yearlings, and every year, all of those populations will grow by 10%. So as our summary concludes, we can say as t approaches infinity, any initial state vector, any realistic one anyway, that gets multiplied by a to the t will point in the direction of the eigenvector v1 of the dominant eigenvalue. So it'll point in this direction in three-dimensional space. For each additional year thereafter, the state vector will grow by about 10%, which is the 1.10 growth factor. So for every 100 adults, the ratio will remain the same, because even if we multiply all of these by 1.10, or 1.10 to the 100th for that matter, the ratio of 0.38 to 0.21 to 1 will still be there. Because when you scale a vector, you don't change its slope, you just scale its components. So for each additional year thereafter, the state vector will grow by about 10%. For every 100 adults, we would expect 38 calves and 21 yearlings. And so that concludes us working with this. Again, all we really need to look at is the dominant eigenvalue and the corresponding eigenvector, and that will tell us what's going to happen in the long run.